Yeah, welcome. Good morning. I hope you had a pleasant night. My name is Benjamin, and today I'm talking about evaluation of low-cost microcontroller-based electronic systems for simple sensor node applications. So first of all, just briefly introduce the term of monitoring. I think you're all kind of familiar with that. Monitoring is nearly everywhere, sometimes noticed, sometimes unnoticed, but probably more interesting are these systems which are unnoticed. Some examples, you have it, for example, as the ABS, the emergency braking system in your car, or maybe also systems for keeping the distance, and many, many more. There's something for watering plants, keeping track of your house, whatever. There are many, many examples of where this is happening all the time. So then is the first question, why it is so important. And yeah, the answer is quite easy. We don't want to have such things. This is a collapse of a building in Cologne in Germany and one in the USA. And on the first one, 2 people died, and the other one, I think 96 something people. And evidence showed afterwards that there were things happening before. So just if we had monitored such a building, we could have avoided this and saved these lives. So this brings me directly to monitoring nowadays. I think you're all kind of familiar with Raspberry Pis. Maybe you can just lift up your hand who has already worked with that. Okay, wonderful. So yeah, you know, this is a cheap little computer, something around 40 euros. Nowadays it's a little bit more expensive because of chip shortage, but a very capable device, 4 cores. You can add an SD card for storage. It's just the size of a computer mouse. It has wired and wireless connections. And you have a Linux operating system. You are free to do whatever you want. If there's a compiler, you can run it. And by researching, I had some things on the slides here. It was used in the offshore wind industry, for example, to monitor these wind turbines, and also used for a project in tunnel production, tunnel digging. Quite interesting approaches, but they all use these single-board computers. And this directly brings me to our motivation. These devices are nice, but at some point they have also some flaws. They are powerful, yeah, true, but sometimes they use a lot of energy, and sometimes you even need to go a little bit smaller. So then the idea came up, why shouldn't we go with microcontrollers? They are also powerful, they are very reasonable priced, something around 5 euro. If you order it in China and have some time, then you can also get it for even less. So also good scalability. They have a small footprint, as I said, and they're also good for educational purposes. So we did a short market research, and there are really a huge number of devices out there, and we collected 34 microcontrollers, 27 single-board computers, with a price range of 5 to 150 euros, probably nowadays a little bit more expensive. And then we nailed it down to 3 and 5 of these devices. You can see them in the images, some of the Raspberry Pi family, and the black ones on the right, lower side, these are the ESP ones. And if you have such devices, then you need to have some kind of metric. So what is this defining thing where it says, okay, it's capable of doing what I want to achieve? And so we said, okay, first of all, we're talking about power. Maybe if you want it for a battery-operated scenario, then power is important. So we are measuring the current draw in different situations. Second one, it's quite important to choose the right programming language because of speed. And so we said, okay, we have to have a benchmark which is capable of showing out how this performs. So we said, okay, we will test all primes, or try to find all prime numbers until 1 million, and then just record the time. And as we also wish to transfer these data wirelessly, it's also interesting how much data we can send out just in a regular way. And so we are generating some random character strings and send them within a message, and then also record how long this takes, so we can get an estimate how many messages we can send per second. So let me show you some results. If you're interested in more detailed research, just have a look on the paper. There's a table with more detailed numbers. I just don't want it to bore you with these numbers, so I just picked out some of the interesting ones and put it here in this graph. So what you can see here, green is idle. So idle is the state where the computer is doing literally nothing. And you can see these single-board computer Raspberry Pi models. They are something around starting from 100 milliamps to 400 milliamps, quite a lot of current. So you are training the batteries quite fast. And if we do the benchmark, it gets even higher. For these Raspberry Pi 4 models, we are close to 900 milliamps, so this is very much current draw. And then we have the network, just sending out these network packages. It's not that high as the benchmark, but you could also combine them and it gets even higher than the benchmark itself. But interestingly, there's also a sleep mode. This is this little black one. You can just see them very small things. These single-board computers, they have no sleep mode. They're just on or they're off, but they cannot sleep. But these microcontrollers can. And the interesting thing with that is reducing the amount of power by something around a factor of 10. So we're talking about maybe 5 to 10 milliamps to, let's say, 50 or 80 milliamps in just the idle mode. And now to the results for the programming languages. I think you all have guessed Python is not the fastest. There's also a difference in how these languages work. You can definitely see Python is way slower. And we're talking about a ratio of 27 to 70 times slower, depending on what you're doing, depending on which device you are. So, yeah, main fact here, if you're up for speed and doing lots of things, then probably C++ is your choice. If you're more in the ease of use, then probably Python is also okay. Interestingly, the ESP32 performed in the C++ test close to the Pi 0. So the Pi 0 is an 800 megahertz single core chip, and the ESP, as you can see here, just ran in 160 megahertz, and they're coming out around three-ish seconds. So quite interesting that such a little €5 device is also capable of competing with the Raspberry Pi 01. Then for the Wi-Fi performance, I have 1,100 characters in these messages, and you can see I just did the test for the both ESP models with the same CPU speed. And yeah, we were something around 20 milliseconds. So this means something around 50 messages per second, kind of. And the thing is, like, if we have a wireless transmission, there's always the thing of, okay, what is the minimum, what's the maximum, and you can see these bars show or indicate that there's a huge variety in the time needed for transmitting a message. So sometimes you're also needing 200 milliseconds, and it's just probably 5 messages you get through per second. But this is really up to what you're going for. If you need huge throughput, then maybe you should also think of if there's a better way. Then let me briefly introduce how the system itself looked like. We went with a kind of abstract design, so this is probably not a very new one, or it's not the invention of us. It's just like sorting out these things. We have the microcontroller itself, we have a gateway, we have a server, and we said, okay, we want to have all these things as kind of building blocks, Lego things, where we can say, okay, I want to have a certain power supply, I want to have a certain application, I want to also be able to come up with different sensors, and also like be able to specify how these data will be transmitted. And here's the actual design we used for the experiments I will show you in a second. We had these ESP32 and 8266 ones. They were running C++ application. We used the I2C bus and the GPIO for some sensors. I will show you an image in a second. The data was packed within a JSON package, so everything was in there. It was transmitted wirelessly via Wi-Fi to a router, which handed it over to Raspberry Pi being the server. And they run an own Python server, and it stored everything on the SD card. But you are generally free to do it whatever you want. So you're not limited to, for example, using Python or C++. This is how the setup looked like. You have a battery pack, voltage converter, the microcontroller itself in the center, the different sensors, and also a voltage voltage and current measuring sensor, so to get an idea of what's happening with the device. So now let me show you some of the results we have done. So we said, okay, with this platform we want to do some experiments and just compare stuff and check if this is a valid approach. So here you can see the plot of the voltage, battery voltage against time, and here you can clearly see that like the deep sleep is a really great function. So if you don't use that, if you just do it and do a sleep in terms of burning the energy, the ESP32 just came out with 1.5 days, and the 8266 one with 3 days. But if you just make them deep sleep, it lengthened the time of operation until 6.5 days, which is quite interesting for just 4 regular AA rechargeable batteries. And just go ahead and have a look on some of the sensor data. We had also some temperature and illumination sensors, so it was the question of maybe place one in one room, one in the other room, so one facing north, one facing south, and then have some evaluation on that. So you can clearly see the blue one in the first is the temperature of the room facing north, the other one is the facing south. You can see that like when the sun comes around, it's getting hotter. So I think it's not hard to say, or hard to see. And below you can see the same with illuminance. So illuminance means the amount of light coming on a certain area. And yeah, obviously as the sun comes around, there's more light. And the same as I said before, because of these limitations in battery, the blue one, this is the ESP32, just came out around 2 days-ish. So this brings me to the question, which one is better? And the clear answer is, it depends. If you have to have an operating system, so if you have, for example, things to install, things to do, which you can't do on these limited resources of a microcontroller, then probably you're good with a single board computer. If you need a certain language which is not capable of creating these binary files for a microcontroller, again, probably you should go with a single board computer. If you use special USB hardware, again, the single board computer. And also display output, if you need it, probably then you should go with the single board computer. But on the other hand, if you're in for cheap devices, then it's definitely a good choice to go with the microcontroller. It has many interfaces, so digital and analog one. And probably there's also devices with special interfaces if you need them. So just have a look and probably you will find something. And they are really good in terms of power. So if you're just out for collecting some data and sending it over on some kind of schedule, that's probably the thing to go to. And I will end up with some outlook. Yeah, this was just a brief lookout on what we did. But there are so many more things we can do. For example, like have a look on real-time clocks, just to arrange things within these packages. Maybe using UDP instead of TCP, so not waiting for the answer coming back. We could also think of alternative wireless connections. So yesterday we had a talk about LoRaWAN, for example, if you're in for very wide area communication. Also interesting, these little devices are offering libraries for mesh networking, so they're building up a mesh. They don't need to care, they're just organizing themselves. Quite interesting. Also probably a nice idea is a custom PCB, so own printed circuit board that you can arrange stuff, because these power consumption things is not as good as the manufacturer claim, because every of these devices is built up to a certain testing out board, so you can even go lower if you do an own PCB. And also, if we are talking about these things being in the field, sometimes there has to be an update. So probably you don't want to plug in your USB on all these devices. So I think there's lots of things to do. And this brings me to the end of my talk. Here are my sources if you're interested. And thank you for your time, and I'm open for questions now.